Hey everyone, my name is Dennis, and I'm one of the mentors here at McMaster Outreach. Today, we will be continuing to improve our coding skills by learning about recursion, and how to implement it in Elm using this new concept called if statements. Now, as usual today, we're going to be working in the animation slot. To start off, what is recursion? Well, basically recursion is a function. But wait, hold on, you say. What is a function? Well, you can think of a function as something that takes an input and puts out an output. Inputs are kind of like the ingredients that you put into a function, and output is like the final product that comes out from the function after you put in the input. A real-world example of this would be an oven. So, suppose, for example, that our function is oven. Then, say our input is cake dough. In that case, our output would be cake. Now why is this? Because when you put the input in the function, an output comes out. In this case, when we put cake dough in an oven, cake comes out. Now, let's say, for example, that we wanted to change the input, but keep the same function. What would happen then? Well, let's say the function is still oven. And this time, instead of cake dough, let's make the input cookie dough. In that case, the output would no longer be cake, since putting cookie dough into an oven doesn't produce cake, it produces a cookie. So our output is just cookie. Okay, so that's a real-world analogy of what a function is. But what about a more mathematical example of that? Well, we can do that too. Let's say, for example, that our function, instead of oven, is now addition. Okay, and let's say our input are the numbers 1 and 2. Well, if our input is 1 and 2, and our function is addition, what happens to 1 and 2 when you apply the function addition to it? In other words, what happens to 1 and 2 when you add them together? Well, 1 plus 2 is equal to 3. So our output is 3. Okay, let's change that up a little bit. Let's say our function this time is multiplication. And let's say our input is still 1 and 2. Well, in that case, what would our output be? It's certainly not 3, since 1 times 2, or 1 multiplied by 2, is not equal to 3. It's equal to 2. Therefore, our output is 2. Okay, back to recursion. Recursion is not like any other function. It's a special type of function that calls upon itself. Now, what do I mean by recursion being a special type of function? You see, normal functions will take an input and put out an output and simply end there. However, recursive functions will give you a set of instructions to follow, and somewhere in that set of instructions, usually on the final step, there's going to be a step that says, do the same function again, from the beginning, but this time change the input slightly. Now, changing the input slightly in recursion usually means subtracting by 1. In other words, whereas a normal function is just a set of plain instructions, recursive functions include a step that says something along the lines of, do it all over again, but this time make it smaller. Okay, so that might have been a little bit abstract and maybe even a little bit confusing. So let's go ahead and see a real-life example of this. As you can see here, we have a painting where a giant hand paints another painting. But inside that painting is an even smaller hand that paints an even smaller painting, of an even smaller hand that paints an even smaller painting, and so on and so forth until there's no longer any space to paint tiny paintings. Now the size of each hand gets smaller with each painting, and the thing painting each new painting/hand is the previous painting/hand. So basically you have a painting within a painting within a painting and so on, where each painting is done by the previous painting. That in essence is what recursion is. Okay, so now that we've seen a real-world example of recursion, let's talk about using if statements now to actually implement this example. But wait, you say. What are if statements? Well, if statements are actually something you encounter all the time in your everyday lives. An if statement always consists of exactly 3 parts: if, then, and else. If is the condition that needs to be met for the then statement to be run, and else is what happens if the if statement is not met. If that seems abstract, then don't worry. Here are some 3 real-world examples of that. If Michael doesn't do his homework, then he doesn't get to play Roblox. Else, he does get to play Roblox. In other words, old Michael here chooses to do his homework, then he does get to play Roblox. And if he doesn't choose to do his homework, then he doesn't get to play Roblox. Let's see another example. Let's take the game of tag. If Sally catches me during tag, then I am it. Else, I am not it. Pretty straightforward, isn't it? For our final example, let's look at our painting. This might be a little bit more complicated. Okay, so what's happening here? Well, basically what's happening is that as we paint new paintings, we keep doing more paintings inside those paintings as long as there's space left. Okay, so that's the key point here, is that as long as there's space left. In other words, we would write something along the lines of, if there is no more space left, then don't paint any more paintings inside the painting. Else, paint more paintings inside the painting. Alright, so those are some real-world examples of if statements. But let's talk about using this whole recursion and if statement thing in Elm. Say, for example, I wanted to make 12 squares in Elm, but I didn't want to just make 12 squares. I wanted to make each square inside the previous square and decrease their size by exactly 5, as well as rotate them by 3 degrees each time. How would I accomplish this? Well, there's the tedious, difficult way, which is how we've been doing it the whole time, which is basically just making a bunch of squares manually and manually changing their size and manually rotating them each time. And that's how we're going to start off doing it before I introduce you to the recursive way. Right, so let's start writing this code using some of the methods we've learned before in the past. To start off, we have the empty MyShapes model. We then create a definition. Let's call it fallingSquares. And let's also call that definition inside the main function. Let's start creating the first of our 12 squares. Let's make it a size 60, and let's also give it an outline. Let's also give it a rotation, and let's rotate it by, say, 36 degrees. But hold on. Since we want to create exactly 12 squares, and we want to be decreasing the degrees of rotation by 3 each time, and the size by 5 each time, let's rewrite both 60 and 36 as products of two multiplicative numbers. So instead of 60, we're going to want to write 5 times something, since we want each square to be smaller by 5 each time. Instead of 36, we're going to write 3 times something. So what times 5 is equal to 60? Well, that would be 12. And what times 3 equals to 36? That would also be 12. So if you're wondering why I'm doing that, remember that computers will do multiplication for us. So there's no need to manually write down the exact numbers each time, like 36, 33, 30, 27, and so on, if we want to decrease the rotation by 3 degrees each time. Instead, we can simply write 3 times 12, 3 times 11, 3 times 10, and so on. Alright, so we have our first square. Let's go ahead and compile that. Mission complete. Now let's write our second square. Since we want the second square to get smaller by exactly 5 units, we don't need to write 5 times 12 this time. We're going to write 5 times 11, which is equal to 55. Since we want the degrees to get smaller by 3 this time, we don't need to write 3 times 12. We're going to need to write 3 times 11, which is 33, which is 3 less than 36. That's what we had before. So let's go ahead and compile and see what happens. As you can see, we have a second square that's a little bit smaller and rotated a little bit less. Let's go ahead and make that third square. Okay, once again, we're going to want the third square to be 5 units smaller than the second square. So instead of 5 times 11, we're going to do 5 times 10. And instead of 3 times 11, we're going to do 3 times 10 here for the rotation. Let's hit compile and see what happens. Yep, once again, we have what we want. And let's do that for the fourth square. Okay, so hopefully by now you guys have noticed the pattern to how I've been writing these squares. The pattern is that the only thing that's really changing when altering the size and the rotation of the new squares is the counter, which by now is at the number 9. So now I'm going to just copy and paste this whole thing until we get to our smallest possible square, which is going to be of size 0, aka 5 times 0, at which point we'll have made our 12 squares. But wait, you say, why on earth would we change this into multiplication? Like, why not just subtract by 5 each time manually? Isn't that easy to do? 60, 55, 50, 45? Yeah, okay, I'll admit, it is easy to do. But imagine if we wanted to get the squares to get smaller by 0.25342 each time. Would it be easy to do that subtraction then? Of course not. But would we still be able to write something like 0.25342 times 12, then times 11, then times 10, then times 9 each time? Yes, that would be much easier to do. So let's go ahead and finish this. As you can see, I'm simply making the counter smaller by 1 for each square. Nothing else fancy is going on here, just making the counter smaller by 1 each time. Let's hit compile and see what we have. Nice. So as you can see, this is a little bit tedious to do. And in fact, if we wanted to do this with 100 squares or 1,000 squares, it wouldn't be a little bit tedious. It would be incredibly tedious to do. Like, imagine copy and pasting that 1,000 times and then changing each number 1,000 times. Nobody really has time for that. So let's go ahead and try this the easier way. With recursion, we're going to want to create some sort of statement along the lines of, if there are already 12 squares, then don't do anything, since we already have the 12 squares that we needed. Else, create a new square that is 5 units smaller than the previous square, and rotate it 3 degrees less. So let's go ahead and comment that out in order to help us write our actual if statement, and let's comment out the super tedious function as well to help us write our recursive function. Now that we understand the concept of if, then, else statements and recursion, let's actually go ahead and write that same fallingSquares function, but this time in a recursive way. As usual, we will need an if, then, and an else. But what do we actually write here? Well, let's start with the if statement. What does it say down here? If there are already 12 squares. Another way to interpret this is to say if the counter has reached 0. Since when the counter does reach 0, we will have counted down 12 times. So let's go ahead and write if counter double equals 0. Note here that I just wrote the double equal symbol. That's because this is a way to ask the computer to see if two things match. In this case, we're asking the computer to see if counter matches the number 0. Note also that because I've created a new counter variable on line 9, I'm going to need to tell fallingSquares to expect a counter input on line 6. Okay, so what about the then part of the statement? Once again, we're going to use this as a guide. What does it say down here? It says, then don't do anything, since we already have the 12 squares that we wanted. In other words, we can probably just write something like group, open bracket, close bracket. Why? Because that's just going to take whatever we have and just group it together and do nothing else, which is exactly what we're going to want to do. How about else? How do we want to write this else statement here? Well, if counter is not equal to 0, in other words, if there are not 12 squares, then we want the else part of the statement to print out a square and then rerun the whole thing again, this time using counter -1 as the input. Let's actually go ahead and go back to our tedious function here, copy it, and paste it here in order to help guide us write the first square. Since we want counter to be some kind of number that starts at 12 and counts down by 1 each time, we can simply replace all the 12s here with counter. That way, on line 3, when fallingSquares asks for an input and we put the number 12, the very first square will be of size 5 times counter, aka 5 times 12, since 12 is counter. Similarly, it'll be rotated by degrees 3 times 12. Let's hit compile now. As you can see, that gets us our first square, but we need to be able to write the remaining squares. This next step is called the recursive step, and it is by far the most important part of the entire process, so please pay close attention. Instead of writing out a bunch of squares like we did earlier in the tedious function, we're simply going to call fallingSquares again within the else part of the statement. But this time, instead of having an input counter, we're going to have an input counter -1. Note also that because there are now 2 objects here, we're going to have to group them together. And as you can see, when I hit compile here, we're actually going to end up with the exact same thing as our tedious fallingSquares function, except in way less lines. Okay, so what is actually happening here in the recursive step? Well, let's go through it. As you can see on line 3, the initial input is 12. In other words, counter is initially equal to 12. That means that this part of the statement gets checked. Does 12 equal to 0? Obviously not. So then this whole thing gets skipped, which means the else part of the statement gets ran. First, a square of size 5 times 12 is created, and it's rotated by degrees 3 times 12. That was the first square you saw earlier. But now a second square gets defined. This time it gets defined using fallingSquares, aka this whole thing, but with the input 12, remember that counter is equal to 12, -1. In other words, the new input, the new counter is 11, not 12. So now counter double equals 0 gets checked. Obviously 11 is not equal to 0. So then the else part of the statement gets ran again. A square of size 5 times 11 gets created, and it's rotated by degrees 3 times 11. Then another square gets defined, but this time with the input 11 minus 1, which means that the input now is 10. 10 does not equal to 0, so then it doesn't get grouped like this. Instead, a square of size 5 times 10 gets created, and it's rotated by degrees 3 times 10. And then so on and so forth until finally this part is true. And when it is true, then the then part of the statement, aka do nothing and just group all the squares together, finally gets executed, and we're done with our fallingSquares function. Suppose for a moment that I change this initial input 12 to an input of 1. What happens then? Well, counter would initially equal to 1. So then this part of the if statement gets run. Does 1 equal 0? Of course not. So then once again we go to the else part of the statement. A square of size 5 times 1 gets created, an outline is given to it, and we rotate it by degrees 3 times 1. Then fallingSquares gets called again, but this time with the input 1 minus 1, aka the input 0, which means that the new counter in the next step is 0. Therefore, on line 9, when the computer checks once again if counter is equal to 0, it'll finally be true. And then all that's going to happen is we're going to just group that one tiny square we already have. So let's hit compile and see that in action. As you can see, like we predicted, just one tiny square is on the right side of the screen. Similarly, if we were to have changed this to, say, 5 squares would be created. 12, like we had originally, would mean 12 squares. As you can see, writing out this code required way less effort. You might be thinking, well, isn't this more complicated? I'd rather write out 100 lines of code than have to think about recursive steps and all that. Why not just write out 12 squares? Isn't that way easier? You might be saying, well, perhaps, but imagine if you wanted to draw 30 squares, or 50 squares, or 100 squares. It wouldn't really be all that easy to copy and paste that many times. Clearly, it would be much quicker to simply use recursion. On top of that, recursion also allows us to have more flexibility. If I suddenly wanted to change the number of squares on the screen, instead of having to copy and paste it a bunch of times and delete all my lines, I can simply change this initial input number. Say, for example, I wanted 2 squares. I would simply change this to 2. If I wanted 30 squares, I would change it to 30. Heck, if I wanted 100 squares, I would simply change this into 100, and we would be done with it. Okay, so that's the basics of recursion. Now let's move on to a bit of a cooler example. So I actually have some code prepared for this part. It's basically just the flower code from lessons 2, 3, and 4. Remember that in those lessons, we created the following flower. While this looks pretty cool, let's say we want to create an even better flower. Say we want this flower to change colors as the petals grow bigger, and maybe rotate the petals a little bit as well. How would we do that? Well, once again, we're going to be using our friend Recursion. Let's first take a look at that old flower code here. Notice that it expects color as an input. This is the part we're going to be manipulating via recursion. Let's go ahead and start writing that recursive function now, actually. Let's call it superFlower. Like fallingSquares, we're going to need it to expect a counter. And like any other recursive function, we're going to need an if, then, and an else. We're going to want something along the lines of, if counter is equal to 0, then just group everything you already have together, else create a flower of a certain shade, scale to a certain size, and rotate it by a certain amount, all influenced by a changing counter variable. Then do the same thing again, just this time with the counter -1 as an input. Okay, so let's do that step by step. The checking to see if a counter equals 0 can be written just like in fallingSquares, is counter double equals 0. The then part of the statement, which is just group everything together and do nothing else, can be written just like in fallingSquares as group open bracket close bracket. Now the else part of the statement is where it gets a little bit tricky, but let's start with creating our initial largest flower. However, instead of saying something like flower red, we're actually going to be using HSL here. Why are we going to be using HSL? Because we're going to be wanting to change these numbers inside so that the flowers can actually change color as counter changes. Here I've arbitrarily chosen HSL degrees 0, 1, 0.5, which should give us a color of red. Don't forget that since we're going to be doing recursion, we're going to want to group this as well. Okay, this isn't really going to cut it though, because as you can see here, nothing is going to change no matter how many times I run this. So we're actually going to have to change one of these numbers here into something to do with counter. Let's actually go ahead and change the lightness. Instead of a boring static number like 0.5, let's do something more dynamic like 0.05 times counter. That means each time counter changes, the shade of the petals is going to change. How specifically does it change? Well, each time counter decreases, the shade of the flower will get darker and darker and darker. Let's actually go ahead and couple that with the scale function. Let's do scale of 0.1 times counter. What does this mean? Each time counter decreases, the flower gets smaller and smaller and smaller. So combining these two lines, what are we really saying here? We're saying that each time counter counts down by 1, a smaller, darker flower is going to be created inside of the flower that's already been created. In other words, it'll look like the flower is spawning a bunch of petals from the center point that get lighter and lighter as the petals grow larger and larger. Let's also do something like rotation as well. Let's say we want to rotate it by, say, degrees 30 times counter each time, just to give it a bit of vibrance. That way, each time a flower is created, they all have different angles of rotation and it looks more natural. Let's not forget the most important part here, which is actually the recursive step. Just like in fallingSquares, we're going to be calling superFlower, but this time, instead of counter as the input, we're going to have counter minus 1 as the input. Similarly to our fallingSquares function that we created just now, what this is going to do is going to run superFlower over and over and over again until finally counter equals 0 is true, at which point we'll group all the flowers we have together and our function will be complete. Okay, so let's actually go ahead and see that in action. Say we do superFlower 1. 1 flower gets created. Say it was superFlower 3. 3 flowers will get created, and so on and so forth. As you can see, these flowers clearly look way cooler than our original flower. Not only is it way cooler, but it also allows for way more flexibility. If I wanted to say write 12 flowers, I could simply change the input number, just like in fallingSquares, and I would get a completely different flower. This concludes our lesson for recursion. As an extra challenge, try to create a recursive function where a bunch of squares are on top of each other, with darker squares at the bottom and lighter squares at the top. This is what the final function should look like. And here's some skeleton code to get you started. As you can see on the left side of my screen, you'll need to use the concepts we learned today about if statements and recursion in order to create the recursive function that is used to create the squares on the right side of my screen. Take a few minutes now to pause the video and attempt this yourself before I give you the answer. Did you manage to get it? If you did, congratulations. It means you really understood the concepts taught to you here today about if statements and recursion. And if you didn't, don't worry. Recursion can be a difficult concept to understand for most people, and it often takes several tries and attempts to really grasp it. You're more than welcome to watch the video again or try this problem again. Either way, here's the answer. Hopefully you guys enjoyed today's video and you really see the importance of recursion. It can really be a lifesaver when it comes to having to do tedious tasks that nobody, including yourself, have the time to do. This pretty much concludes our video. Thank you guys for watching and have an amazing day.